Hey everyone, I'm Neil, and in this week's edition of the mini lecture series, we'll be covering shortest paths as well as greedy algorithms. And so in shortest paths, we'll start with a quick review of Dijkstra's and get into the Bellman Ford algorithm. So to begin with, last week you learned about Dijkstra's in lecture as well as in the homework. Essentially, to really quickly overview how it works. We're trying to find the shortest paths from a start node to all the other nodes in a graph. And so what we do is we initialize all of the other nodes to infinity first. Here, we construct a priority queue, and we process nodes off this priority queue based on the shortest paths so far, right? The closest node so far. And so every time we, that's what we do here. So every time we process a node, we look at all of its edges branching out. We update the distances. We update distances. So I'll nickname this procedure, these two lines, as kind of like the update procedure, right? We're seeing if any of the distances we know so far can be decreased. And then what we do is, we keep, going through that procedure, iterating through all of the vertices until our priority queue is empty. And that's kind of how Dijkstra's works. It'll give us the shortest paths. But an important thing to note with Dijkstra's is the input requires that, it says positive edge lengths, or essentially, more accurately, non-negative edge lengths, right? Why is that the case? First of all, it's an issue because in graphs with negative edges, will Dijkstra's work? Will Dijkstra's not work? We're going to have to explore that, right? And so if we look at this example where S is our start node, and let's say we want to get to, let's say we run Dijkstra's on this, right? So what's going to happen? In our priority queue, we'll first input S with distance 0, because that's our start node. A with distance infinity, and B with distance infinity. So now we go through this procedure while the priority queue, that is really ugly. So we go through this code. The first thing we do is we delete the minimum node from the priority queue. And here the minimum node is S, right? Because that's our start node. And so we look at all of the edges going from S to other places. We see S to A, we get that to be 3. And so 3 plus 0 is 3, is clearly less than infinity. So we're going to update A to be 3. And the same with B. B will become 4. And we've deleted S from the priority queue. So we're kind of done with S. So now what do we do next? The next closest one, the next thing we pop off the priority queue or we delete is 3, because that's the smallest number. And so there's no edges going out from A, so we don't really do anything at this step. But again, we've deleted A from the priority queue. And so from B, so in the third iteration of Dijkstra's, we still have B4, but the other two are kind of popped off the priority queue. They're kind of finalized almost. And so when we look at B, when we process B off the priority queue, what we're going to do is there's an edge from B to A for -2. So we would have wanted to update A's distance to 4 minus 2, which is 2. So we wanted to do A, and we wanted to set it to 2. But the reason we can't do this is because we've deleted A from the priority queue itself. And so saying this decrease key won't really work, because we can't decrease A's value, because A isn't even in the priority queue anymore. And that's kind of like, that leads to the issue, right? So even though the shortest distance should be 2, we've already finalized the shortest distance to be 3. And so that's the issue with Dijkstra's, with graphs with negative edges. The problem arises because of the fundamental assumption that Dijkstra's make. And this assumption states that, Dijkstra believes that adding on edges in the future would only increase the cost, right? No edges in the future would help decrease the cost. And so I've kind of summarized that in here. Dijkstra relies on the fact that adding an edge can never make a path shorter, right? But we've seen with a graph with a negative edge weight, that's clearly false, right? So what does it say? It relies on the fact that adding an edge can never make a path shorter. In this case, adding an edge can make a path shorter, right? Therefore, it can decrease it. And so that's the issue with Dijkstra's. So again, these are the two paths. Dijkstra's assumes that the shortest path, a path that's longer in terms of like the number of edges, it's basically saying this edge B to A would not be able to make the path shorter, when in reality, that's not the case. And so if we do come across graphs with negative edges, we're going to need to figure out an efficient way to kind of explore all the possible paths to that destination, right? And what do I mean by that? What I mean by that is, in this graph, if we had explored the S to A path, as well as the S to B to A path, those are kind of like all of the possible paths from S to A, right? There's no other possible paths. So if we had explored all of the possible paths before returning an answer, or before finalizing that the shortest distance to A was 3, then we would have been good, right? We would have returned the correct answer of 2 being the shortest path, the shortest length. And so if we had a way to kind of explore all the possible paths from the start to the destination, then we could kind of compare those, all those paths, and see which one is the shortest distance. But yeah, so that's kind of setting up some of the groundwork as to why Dijkstra's doesn't work, why Dijkstra's doesn't work in all cases, and kind of giving the motivation behind the next algorithm we'll see, which is the Bellman Ford algorithm. We need to find an efficient way of exploring all the possible paths. But if we want to look at all the possible paths from a starting point to an ending point, we might have to explore a ton of different possible permutations between edges, which will lead us to many different possible paths. So before starting, before diving into our algorithm, let's look at one more important fact to note here. So if we have this example graph from, and we want to get from node S to node E, one possible path could be, S to A to B to E, which is kind of like going through 3 edges, right? 3 edges. We could also go from, let's say S to A to C to D to B to E. And this kind of goes through what, like S to A, 1, 2, 3, 4, 5 edges. But would we ever want to explore S to A to B to back to C, and then back to A to B to D? So let me write that out. So would we ever want to go from S to A to B, C, A, B, E? Because this has S to A, 2, 3, 4, 5, 6 total edges. But the thing is, as you see, or let me change to what that's going to result in is a path that looks like this. We'd cycle back around and then go to E. So would we ever have this type of cycle, cyclic motion? We're kind of, and the answer is no, right? With an asterisk, which I'll get into later. But the answer is no, because cycling through nodes that we've already seen before is only going to increase our work, right? Because if we have already been to B, why would we want to go back to C and then up to A and through B again? That would only seem to increase the work, right? And I will note an asterisk there, which we'll get into later on. But Actually, let me do this first. So asterisk is, we might want to do that cyclic motion if there's negative cycles, which we'll get into later. But yeah, essentially what that's saying is that we would never want the length of the path to exceed, be 6 or greater, right? And where did I get this number 6 from? There's 6 total vertices, right? 6 total vertices. And if we want to get from S to E, at most, we would want to go through every single vertex once, right? The moment we exceed that and we explore a vertex twice, it seems kind of, pointless almost. We're adding on extra costs for no reason, right? We've already been to that node. We don't want to go through that node again. So that basically means that the shortest path, so if we have this statement, right, the shortest path won't exceed blank number of edges, right? That number of edges, that value in this case is going to be 5, right? It won't exceed 5 edges because at most you'd want to explore every single node. So the connections, the edges between them is going to be 5, right? There's going to be at most 5 edges. And an example of that I wrote down here, S to A to C to D to B to E, right? And so this number 5, in terms of a more meaningful expression, would be the number of vertices we have minus 1, right? We know our shortest path is limited to v minus 1 edges total. And so the Bellman Ford shortest path algorithm builds on that fact, right? So essentially what we want to do is, going back to this original graph that we had, we want to explore all of the edges a certain number of times, right? By exploring all of the edges a certain number of times, we'll be able to ensure that we explore all of the possible shortest paths. And so how many times do we want to explore all of the edges? That just becomes v minus 1. And so if we look at the pseudocode for the Bellman Ford algorithm, it's actually pretty, compared to Dijkstra's, it's even a little simpler, right? We initialize all the distances to infinity as usual, except for the starting node, we initialize that to 0. Then what do? We iterate v minus 1 times. And every single time we iterate through, we examine all the edges. And we do this update operation. And so the update operation I kind of went over earlier, we do that exact same update operation in Dijkstra's. It's basically looking at, how long does it take to get to this node? How long does it take, and compare it to how long does it take to get to another node plus the length, the edge length between those two. See which one's shorter and update accordingly, right? And so that's pretty much all Bellman Ford does. And so if we examine it on, a new graph, let's look at this graph, for example. Let's say A is our starting node. Initially, we're going to get, this to be 0 and this to be infinity, etc., right? And so we explore all of the possible edges, every single iteration. So the first iteration, we're going to explore, E to D, C to E, C to D, B to D, etc., all of the possible edges. But most of the possible edges, right? Let's say we examine B to D first, right? What we're going to try doing is we're going to check we're going to do this operation. We're going to actually distance to D. We're going to check whether the distance to D that we have so far is less than or greater to the distance to B plus length of B to D. And this is exactly what the update operation did. But the thing is here, the distance of D is infinity because we haven't really done any work so far. The distance to B is also infinity plus the length is 2. So this becomes infinity. So we don't really do any update operation. But in the first iteration of Bellman Ford, what we are going to do is when we explore edge A to B and edge A to C, what we're going to realize is edge A to B is going to result in B's distance to be updated to 0 plus 4, which is 4, and C's distance to be updated from infinity to 0 plus 2, which is 2, right? And so After the first iteration of Bellman Ford, it's important to note that, or let me say this first. After the first iteration of Bellman Ford, we've calculated all the shortest paths of length 1, right? So A to B's shortest, so far what we have is the shortest path from A to B, where the shortest path is of length 1 edge. That's just going to be 4. D is still going to be infinity, because the shortest path we have from A to D, as you can see from inspection, it's going to have to be at least 2 edges, right? But we're only done with the first iteration of Bellman Ford. So far, we only know the shortest paths of length 1 edge, right? But the moment we go into 2 edges, what's going to happen is we're going to explore all of these edges once more. B to D is now going to become 4 plus 2, which is 6. Et cetera, et cetera. But then obviously we've already covered A to B and A to C, but we explore those again. They don't really help us out. But the interesting part is when we explore edge C to B, right? C to B is now going to be 2 from A to C plus this 1. So B's distance is going to get updated to 3. So that's kind of the nice thing that happens here in Bellman Ford. As you go through more and more iterations, you're going to get better and better shortest paths. So now after the second iteration, so after iteration number 2, we've found all of the shortest paths of distance 2 edges away from our starting vertex. And so essentially in writing here, we can say that the shortest path of length I edges, right? So after the ith iteration, we've come up with all the shortest paths of length I edges. Now, the important fact to note is that in the future, we might come up with an even cheaper shortest path, but that shortest path might have like, I don't know, I plus 10 edges or something. It could have more edges, because having more edges could, with the addition of negative edges, it could actually help our cost, right? It could actually decrease the cost. But what Bellman Ford guarantees is that after the ith iteration, we know all of the shortest paths of length I edges. But we could potentially improve on them as we add the number of possible edges to these shortest paths. So essentially at the end of this, so afterwards, we'll have the shortest paths with v minus 1 edges. And so this basically confirms that we're kind of done with the algorithm, right? Because as I said here, the shortest path won't exceed v minus 1 edges. So if we explore all the shortest path with v minus 1 edges, we're kind of guaranteed we've had the shortest path. And so looking at the runtime, so we see that we have v minus 1 iterations. So we have O of v number of iterations. And in each iteration, what we do is we iterate through all of the edges. So O of E is the work done at each iteration. And so in total, we're going to result in O of V times E total runtime. And so a lot of times in like dense graphs, we can approximate the number of edges to be of the order O of V squared. So in that case, this entire runtime would be O of V times V squared equals O of V cubed. But a more accurate way is saying V times the runtime is V, the number of vertices times the number of edges. And so if we compare that to the runtime of Dijkstra's, the runtime of Dijkstra's is essentially O of V plus E log V. And so as you can see, Bellman Ford is a little bit more expensive, but we need that extra cost, right? In order to explore all the possible shortest paths to a node, right? That's where the extra cost comes in. So Bellman Ford is slower for sure, but it's more accurate. It'll find us good solutions even with graphs of negative edges. With one caveat that I'll explain. So earlier I made this asterisk of negative cycles, right? And the reason here is that if we have a negative cycle, so by negative cycle, I mean, like, let's say A to B is like 1, B to C is, I don't know, -3, and C to A is like -4. The cost of going through the cycle, A to B to C, would be 1 minus 3 minus 4, which would be -6, right? That would be -6. But when we're going through Bellman Ford, we could, by analyzing the edges like a ton of times, we could potentially like just want to keep on going from A to B to C and cycling through that, because every time you cycle, you decrease your cost by -6. But then the shortest path from S to E would then become like -infinity, right? Because you'll just keep on cycling through this, A, B, and C, and keep on decreasing your cost. And that's a solution that doesn't really make sense, right, in the real world. So essentially, if we ever have these negative cycles, Bellman Ford can easily detect them. All you have to do is, after your algorithm, iterate through all of the edges one more time, see, do any of the, are there still updates going on? Like, are there still things that are decreasing in terms of the distance to it? If there are, that means there is a negative cycle somewhere in there, which will, because the cost is still somehow going down. And so that's kind of like, Bellman Ford provides an easy way of detecting these negative cycles through that way. And so, yeah, that's kind of an overview of Bellman Ford. In the next video, Lily will go ahead and talk about some greedy algorithms.
Thanks, Neil. In this next section, we'll be covering an introduction to greedy algorithms, and we'll take a look at minimum spanning trees from this greedy point of view. So what's the intuition behind greedy algorithms? So greedy algorithms usually go something like this. We take whatever step looks most optimal right now. At each step, you take the local or short-term best choice as a way to find or approximate the global or overall best choice. Let's do an example. Suppose we want to find the shortest path from our root A to some leaf, D, E, F, or G. So greedy will tell us that each step you should take whatever path is shortest to you right now. So greedy will tell us that going from A, the path to B is shorter than the path to C, so we should take that. And now from B, the path to D is shorter than the path to E, so we should take that. So greedy would return for us this path from A to B to D with weight 4. And perhaps you're already seeing a problem. This is actually not the most optimal path. If you take A to C to F or A to C to G, either of them would have weight 3 rather than 4. So, and you'll be right, greedy doesn't always return the most optimal solution globally for us. However, it's still a really, really important idea for a couple reasons. So one of them is that it's often really easy and really fast to implement a greedy algorithm because all the operations are at the local level, so you don't have to deal with global considerations. The second is that in many situations, greedy algorithms either approximate the optimum really well or actually gives us the optimal solution. So actually, many of the algorithms you've encountered from either 61B or earlier in this course have been secretly greedy algorithms. For example, Dijkstra, Prims, and Kruskal's all have some sort of greedy flavor. And we'll see this more in depth in the MST discussion coming in the next section. So, all right, let's look at minimum spanning trees now. When we're talking about this, let's assume that we're dealing with undirected weighted graphs, and let's assume that it's connected. The only consequence to having it not connected is that instead of getting a minimum spanning tree, you're getting a minimum spanning forest. But the difference isn't all that dramatic, so we'll assume that all the graphs we're dealing with are connected. So we want to find a spanning tree on the graph of least weight. By spanning tree, we mean that a tree made from edges in the graph such that every vertex is reached by this tree. There are two really famous algorithms for this problem, prims and Kruskal's. You might have seen them in 61B, and so we'll briefly outline them here, do a quick example, and then the focus of this mini lecture is to actually prove that that these are both correct, that these algorithms actually give you the optimal solution, so that the local process of doing greedy actually is the optimal solution for the entire global problem. Okay. So for Prim's algorithm, we start with any vertex in the tree and call it the tree so far. So we start with vertex A, let's say. Every turn we grow the tree by one edge. Now, what this edge is, well, you take all the candidates are edges from our tree so far to unvisited vertices. So A is the visited tree, and then we take all the edges to unvisited vertices, and of those edges, whatever is shortest, we take that path, we take that edge. So this is how it works, and this process repeats itself. So at vertex A, we see that there are three edges to choose from. The shortest one is either AB or AD, and let's break ties alphabetically, so we'll take AB. We mark B as traveled or visited, and then now the candidates are BE, BC, AC, AD. And we see that BE and AD are the shortest ones. Breaking ties, we take AD. And now our candidates are BE, AC, BC, DC, and DG. Of those, BE is the shortest, so we take it. Know what we're doing here. We're keeping track of what's been visited in green, and then everything that's not been visited are still, unmarked. So now the candidates are EF, BC, AC, DC, DG. We take AC. And now here's something important to note. BC is no longer a candidate because C has already been traveled to. We only care about edges from our tree so far to things that haven't been visited. So BC and DC are no longer candidates, so we're left with EF, CF, and DG. Of those, we have, let's do EF. And then now our candidates are FG and DG. Let's take FG because it's shortest. And we see that all of our edges are marked. All of our vertices are marked, which means that we can terminate the algorithm with the green being the tree that we've determined. To actually implement this, we will need a priority queue with priority determined by these edge weights and a tracker on whether each vertex has been explored or visited. Okay, we won't go too much into the implementation. So now let's talk about Kruskal's. Every turn, we also add the next shortest path, but this time we have no regard for what's traveled so far. So literally anything is fair game. We can take essentially any edge that doesn't make a cycle in our marked minimum spanning tree, and as long as that's satisfied, we can take it as long as it's short. So let's see it in action. We don't have a base point in this algorithm, even though I marked A, because, well, everything's fair game. So let's look. AB is the shortest path, is the shortest edge, so we can mark A and B as traveled to. And then the next one is AD. This is also edge weight 1. Similarly, we take BE and FG. So next, let's suppose we take one of the length 2, AC. And now, notice that we cannot put in CD because it would make a cycle, and that's not allowed in a tree. So the CD is thrown out. What's the next shortest one? Well, EF or DG. It doesn't really matter which one we take. Let's, I don't know, for the sake of being different from that one, let's take DG. And now we're done. So something important to note is the termination criteria for Kruskal's. It's not enough for Kruskal's that every vertex has been traveled to. The tree we have also needs to be connected. So how do we ensure this? Recall from CS170 that for a tree, the number of vertices minus 1 is equal to the number of edges. So since we're dealing with adding edges, we just need to add in as many edges as vertex minus 1. After that, we're guaranteed that, since we don't have any cycles, this entire thing will be connected and it'll be a tree. So that's cross goals. A quick note about implementation. For cross goals, we will need to have a union-find data structure containing all the vertices. So for basically, we put each vertex as its own union-find element, and every time we add an edge, we union those two vertices. Okay, if this sounds remotely unfamiliar, or if you want to just remind yourself of this, I encourage you to look at the textbook. There's actually a very nice explanation as to how to implement both prims and cross goals. All right, so we've seen both algorithms now. So next step is to prove their correctness. We'll do this in 2 steps. We'll start with a lemma. And this is called a min-cut property. What this says is that if you partition all the vertices into 2 sets, so if you divide vertices into sets A and set B such that A and B do not intersect, so there isn't like a vertex that's both in A and in B, and also a union B is equal to B. These are vertices. Okay, and I look at all the edges. So this is A, this is B. This has some vertices in them, and I look at all the edges that go in between A and B. So these are all the edges that have endpoints, one of them in A, one of them in B, and I claim that whatever is the shortest one will be in a minimum spanning tree. So again, we take all the edges that go between A and B, and we claim that any shortest edge, the shortest one, will always be in the minimum spanning tree. Okay, let's prove that. This is a short sketch of the proof. The proof relies on something called the substitution principle. And we'll do a proof by contradiction, which should be familiar from CS170. Suppose, let's call this call this edge small a. Suppose A is not in the minimum spanning tree. Okay, suppose A is not. Then we know that some other edge must be, right? So we know that there exists some other thing, some A prime between that goes from A to B. So there's some other one, let's say A prime here, going from A to B in the MST. Why is this? Consider that A and B are both sets of vertices, and for a tree to connect vertices from A to B, we must have something that goes between. Like there has to be some edge that connects vertices from A to vertices from B. Okay. Then we can substitute A prime for A. So basically, we'll take this MST and we get rid of this edge A prime, and we put in the edge A. So we say that this is still a minimum spanning tree because, well, A and A prime serve the same purpose of connecting stuff from A to stuff from B. So then whatever results from this substitution is still a minimum spanning tree. We get a minimum spanning tree. Okay? But this new tree will have shorter smaller weight than the original. Why is this? Well, the only edge that changed between the old spanning tree and the new spanning tree is that we substituted in A for the old A prime. Which means, and since A is the shortest one between A and B, it means that A is, the weight of A is definitely smaller than A prime, and therefore we have a smaller weight. But that's a contradiction because we assumed that, the original tree was a minimum spanning tree, like minimum. It means there should be no smaller weight that could do the same thing, that could span this entire graph. Therefore, contradiction. So since we get a contradiction, our initial assumption must have been untrue. Therefore, we get that A is always in a minimum spanning tree. Okay, so this is the min-cut property. It's proven a little bit sloppily, but just remember that if you divide all the vertices into two groups, A and B, and take all the edges in between them, then we have that the shortest edge in that set is always in a minimum spanning tree. Okay. All right. Now using this, we will prove prims and Kruskal's. All right, let's look at prims. So the general idea of prims on a high level is that you have some tree so far. And we can say that my set A is all the vertices already in the tree so far. So these are the already traveled vertices that we've marked in solid green. These are the ones that we've traveled so far. And B is everything else. And we have all these edges. So what are these edges? These are edges from the tree so far, the vertices traveled so far, to vertices that we haven't traveled before. So that's our sort of candidate space. And then at return, we pick the shortest one. And this is, this makes sense because from the lemma, from our min-cut property, whatever is the shortest in between the sets A and B should be in a minimum spanning tree. And we realize this by putting in the minimum weight between tree so far and everything else. Okay. So here we've proven that every edge that we added through Prim's algorithm will in fact be a minimum spanning tree. Okay. And since the result actually spans, then we are guaranteed that prims will work correctly. On the other hand, we have Kruskal's. You might be thinking that we need to find some set A and some set B for this algorithm at each step, and you would be correct. We need to find some set A and some set B such that the edge that we're adding in at each stage is in fact the minimum between those two sets. So if you would like, you can pause the video right now to think through what the sets A and B are. And I'll spoil the answer in 3 seconds. Okay, so at each step, at some step of Kruskal's, we already have, some components of different trees lying around. Maybe I have something like this and something like this. So these are, the connected components of our current tree so far. And by adding in a new edge without making it a cycle, we're essentially connecting one of these components to a different component. We're adding in like some connection from between two components. We can treat this as this guy right here being A, and then everything else being B. Then when we're taking that edge, we're taking the shortest edge that doesn't make a cycle, so a shortest edge that leads from A to something else. The minimum edge will in fact be guaranteed to lie in the minimum spanning tree. I know this is a little bit weird, but essentially this just proves that every time we add in a new edge that doesn't make a cycle, we're guaranteed that this edge is added outside of A from A to B, and also that it is in fact the minimum. All right. So what this proves for us is that every edge that we add in the minimum spanning tree is actually a correct edge. And since in the end we span the entire graph with a number of correct edges, we know that our end result from this local algorithm will give us the global optimum. If you would like a more rigorous proof of this is sort of sketched. You can read the textbook and also ask Piazza. I'd be more than happy to explain further. So these are just sort of, I don't know, intuitive ideas of why this works. But for a complete proof of correctness, you might need a little bit more rigor and detail. All right, that's it for now. Thank you.